Okay, so as part of the commanding exercise number 8, part 2, I have asked you to self-study the modeling of heat flow from a body in space, so that you will see how to render the heat equations. Okay, so today I will start with solving heat equation. Okay, so we'll solve heat equation by Fourier series. So the approach is quite similar to the approach in section 12.3 to solve the wave equation before. Okay, so let's see the basic assumption that so we have a bar. Okay, so the bar okay, and the bar will conduct heat. So now, so at this point is x equal to 0, is x equal to L. Okay. All right. So so the basic assumption would the first one is that this bar is a thing. So a thing metal bar or wire of constant cross section. Okay, so along the x-axis at each point x, there is a cross section, right? And we assume that we have a constant cross section. Second, the material is homogeneous. Okay. And the third one, we have so the bar is perfectly insulated laterally, so that around there are, so the bar, if the bar is rectangular bar, so they are 4 sides, right? There are 4 sides, and all these 4 sides, they are perfectly insulated, so that the heat, okay, flows, okay, in the direction, in the x direction only. Okay, so that is the, and the quantity we will study, U, is the temperature of the bar at point x and time t. Okay. The law governing U is the following one-dimensional heat equation. Okay, so would be, so the first partial derivative of U with respect to time is equal to c squared of the second partial derivative of U with respect to the spatial variable x. Okay, so this equation will be denoted as this equation number. And we have two boundary conditions. Okay, so ULT is 0 and U 0. So at the point x equals to 0, right? For all the time, the temperature is 0, and also the temperature at the point capital L, and for all time t, is also 0. And the one initial condition, okay, which is U of x 0 is equal to f of x. Okay, so this boundary condition will be denoted as 12.6.2, and the initial condition will be denoted as 12.6.3. And here, okay, here f of 0 should be 0, okay, because that when x equal to 0, right, this is equal to 0, okay, because of the boundary condition. And the f of L is 0, okay, due to 12.6.2. Okay, so due to the two boundary conditions, so we have these two. All right, so so the initial condition, so this is the temperature at time t equal to 0. Okay, for all okay. So this is our problem. Okay, and so by physics, that there is one unique solution, okay, for the evolution of the temperature along the bar. Okay. Okay, so we are going to solve to render such a unique solution. All right, so now we will follow a similar approach. We adopted in solving wave equation in section 12.3. So the first step is the method of separating variable. Okay. And to obtain, so the two ordinary differential equations. Okay. All right, so we let u of xt to be f of x and the g of t. Okay, so we let, okay. And so now from there, when we take the first partial derivative of u with respect to time, we find that this would be okay. Now, and the second partial derivative with respect to x, okay, comes to be okay. And then by substitution, so we have f of x and g prime t equal to c square f double prime x and g of t. Okay. So now, so we have g prime t divided by gt and c square here, which is equal to, okay, and we let this defined to be k. So k is a constant, okay? K is a constant independent of xt, right? Okay, and so now we have f double prime, okay, f double prime minus k f of x equal to 0, and g prime of t minus k c square gt equal to 0. Okay. Okay. So now we have two ODEs. Okay. The first one is a second order ODE, and the second one is first order. Okay. First order ODE. All right, and now from the two boundary conditions, we have, okay, so we have u0t equal to f0 gt. And the u of lt is equal to fl gt. Okay. Okay. Now, so to have non-trivial solutions, all right, then gt not equal to 0, right? For some t greater than or equal to 0. Oh, this is for all t. Right. Because if g of t is 0 for all t, then by the superior value, the solution is the 0. And we know 0, the trivial solution, the 0 solution, of course, is a solution of this homogeneous linear equation. Right? So we are not interested in trivial solution. Right? So to have a non-trivial solution, then g of t must be non-zero for some t. So in this case, if g of t is non-zero, okay, now we know. But the two boundary condition tells us that these two values is 0 for all t greater than 0. So we have two boundary condition for f of x, which is f of 0 is 0 and f of L is 0. Okay? Is that okay? Now, so now a general solution. So when now it can be seen that for k equal to k greater than 0 or k equal to 0, the only solution okay, so the two, okay, this is so we will say okay, so the only solution, okay, for the ODE in 12.6.4 together with the two boundary conditions in here, okay, is u of t is the okay, it's trivial. Okay, as we have done before in section 12.3, right? So because we deal with such a similar situation, right, in section 12.3. So that we have only a trivial solution. But for k equal to minus p squared, p greater than 0, means that when k is negative, now we have so we have a general solution for the ODE in 12.6.4. So for this, when k is negative, so we have cosine p of x plus b sine p of x. Okay, so we have such general solutions. Okay, now with the two boundary conditions, in 12.6.6, we have, okay, so 0 equal to F0, but F0 give us A, right? So A should be equal to 0. Okay, so A is 0, and 0 equal to F of L, which is equal to B, and sine PL. Okay? Okay, so A is 0. A is 0. And so to have a non-trivial solution, we must have B not equal to 0, so that sine PL is 0. And so this is saying that because P is positive as we specified, so that this means that P is equal to n pi divided by L, and the n is equal to 1, 2, 3, etc. Okay, because P is here, is positive. Okay. All right, so when P these numbers, then we will have a trivial solution. Okay, so we let Fn x defined to be the sine of n pi x divided by L for n equal to etc. Okay. So which are non-trivial solutions? Okay. Of the ODE in 12.6.4 together with two boundary conditions. Okay. Corresponding to K equal to minus n pi L square. Right? Okay, so we find solutions for the first ODE. All right, so now we want to solve the second ordinary differential equation. So for P equal to n pi divided by L, okay, we have G prime plus C square, P square, and G equal to 0. Okay, which is saying that G prime plus C n pi divided by L square and G equal to 0. And we will write this number as n square and g equal to 0, with lambda n defined to be Cn pi divided by L. Okay? And it is the first order ordinary differential equation. And we find so a general solution is GNT equal to Cn and the E minus lambda n square T. Okay, for n. So for each positive integer n, the corresponding constant is p square. Okay, and so so the solution, a general solution, is this one. Okay. Okay. So hence, we defined un to be fn x and gnt, so which is equal to Cn sine m pi x divided by L exponential minus lambda n square and t. Okay. Okay, so that they are solutions of the heat equation in step 1 and so so this I'm sorry, this is step 2, solving the ODEs. Sorry, so this is step 2. Okay. So this part, the second step is to solve the two ODEs. Okay, so we have to solve these two ODEs. All right, so we define U sub n. All right, the product of F sub n and G sub n. Okay, so they are solutions of the heat equations in 12.6.1. So the heat equation we have there, this way. And satisfying the two boundary conditions. Okay, the two boundary conditions in .6.2. Okay, so when you put a 0, un x equal to 0, then fn of 0 is 0, right? So this is 0. Because that here, so if x is 0, this is 0, sine 0 is 0. When x equal to L, when x equal to L here, this is sine m pi, and sine m pi is also 0. Okay, So when x equal to 0 over L, then U sub n x will be 0. Okay, so this is the two boundary conditions we have here. Okay, so UNs are okay, and so but we have one more condition, all right? Initial condition, right? So we have to find a solution which satisfies the initial conditions. Okay? How? So now we have to step 3. So we find the solution of the entire problem. Okay. In 12.6.1, 12.6.2, and 12.6.3. Okay, so we have a heat equation, 2 boundary conditions, and 1 initial conditions. All right, and we will solve the entire problem by Fourier series. Okay, so this is step 3. How to do so? Well, so we let U of xt okay. So we will consider a generic series. Okay, so we consider a generic series, and this is T. Okay, consider such a generic series. And the C sub n hasn't determined yet. Okay, so this is called a generic series. And this series, all right, so so which satisfy 12.6.1. So it satisfies the heat equation and the 2 boundary conditions. Okay, provided that the series converges as well as the series of turn-wise partial derivative converges. To the corresponding partial derivatives of the sum U of xt. All right, so we have to so provided, suppose that we have that the series converges, right? And also the derivative of U, the partial derivative, including the first order partial derivative with respect to time, and the second order partial derivative of u with respect to the x, all right, equal to termwise partial derivatives. Okay. So that this should be checked as we have done in chapter 11. Okay. Right. So that provided this is true, okay, and so now then, so we will check that after we find candidate Cn, okay. So then the initial condition in 12.6.5, 6.3 dictates that u of x0, which is equal to summation Cn sine pi x divided by L equal to f of x. Okay, so the Cn should be, okay, so that should be, so you can see from chapter 11, which is the Fourier sine series expansion of f of x. Okay, and we know how to find Cn. So and the Cn can be computed here. Okay, so okay, so we were, so this is from the Fourier sine series representation of a function. Okay. And the existence and uniqueness, okay, can be established. Assuming that first of all, f of x is piecewise continuous on L, and the second, f of x has one-sided derivatives at all points of the interval. Yeah. Okay, so this, so we have that, and as we know, this is indeed the case when I think when it is continuous. Okay, so we need a stronger continuity is needed such that we have equation. Otherwise, if we have only piecewise continuity of f, then what we have is the average of the left hand limit and the right hand limit of f of x. Okay, so to have the equality. And any questions? Okay, so once we obtain the coefficient, okay, so we will know this series, right? So generic becomes to be specific because we determine the Cn by using this initial condition. Okay, and then we will justify, right? So we will justify that this is series with Cn computed in that way, right? Then we will justify that this series converges, and also the series of turn-wise partial derivative converge too, and converge to the corresponding partial derivative of the sum function. Okay, so once this check-in is done, then we indeed obtain the solution. Okay. Any questions? All right. Now, if no question, there is a companion problem. How about the condition so how about the situation that both ends of the bar are insulated Okay. Insulated means that there is no heat flow from either ends of the bar. Okay, insulation means that. Because in our original problems that at the both ends, the temperature is zero. They are zero, right? At x equal to 0, x equal to L, the temperatures are zero value. But when the two ends of bar are insulated, then right, so we know that the rate of heat flow, okay, is proportional to the gradient of the temperature. Okay, as we know in physics, right? So the rate of flow, of heat flow, proportional to the gradient of the temperature. Hence, if the two ends, okay, x equals 0 and x equal to L are insulated, i.e. insulated means no heat flow. Then we must have okay. So we must have the partial derivative, right, with respect to x. At x equals 0 would be 0, and the partial derivative at x equal to L is also 0. Okay. So now the two boundary conditions, right, becomes to the two conditions, right, described between in terms of described in terms of the first order partial derivative of u with respect to x. Okay. Okay. So they are different from our previous problem. Right. In the original problem, the both boundary conditions that are the temperature at both ends are 0. Okay. So they are different. Okay. And with these two new boundary conditions, you will see okay. So think so with separating variable, okay, this is equal to f prime of 0 gt, and it's f prime of L gt. This implies that f prime of 0 is 0, and f prime L is 0. In order to have things gt not equal to 0 for some t equal to 0. Great. Right. In order to have a non-trivial solution, okay. So the two boundary condition becomes to governing the boundary values of the first order derivative of f of x instead of this. Okay, instead of that. So that in that's okay. That's the that's with 12 with this ODE and these two boundary conditions, okay, and these two boundary conditions equal 12.68, right? So the ODE And these two boundary conditions, we have three cases. K is greater than 0, right? When K is greater than 0, then no non-trivial solution. When K equal to 0, then a general solution is equal to AX plus B, okay, becomes 2. So F prime 0, so 0 is F prime 0, so F prime is A, and is F prime L is also A. So A is 0. So that F0 of X defined to be 1. Okay, is a non-trivial solution. Okay, so when K equal to 0, we have a non-trivial solution, which is a constant. Okay, and K, when K is minus P squared, which is less than 0, and P positive, then a general solution. Okay, so a general solution, f of x, which is A cosine P of x plus B sine P of x, Px, okay, implies that 0 equal to f prime 0. When f prime 0, this gives us that PB equal to, right? And so B is 0. Okay. And 0 equal to F prime L. So this goes to PA. And the sine P of x minus 0. So that we have P equal to pi L n is in n. Okay? Okay. To have, so in order to have non-trivial solutions, so once again, we obtain that when K is equal to minus P squared and P are specific values, then we have non-trivial solutions. And in that case, we define f and x defined to be, okay, to be cosine and L and pi x. Okay, so now we have cosine function. Okay, all right, so I'll stop here. Okay, so two different boundary conditions give us different type of solutions. Okay, and so